Up next is David Leonard. He's a core developer of the Away3D engine, which some of you might know as one of the well-known open source 3D engines written for Flash. He now gives us some insights of a session called The Trick of Light, which will be about shading, I suppose, and lightning. And please welcome David.
Hello. So as Frank said, I'm David Leonard. I'm from Belgium, one of the 3 people from Belgium in total. Most of my time, especially my free time, over the past few years has been spent working on Away3D, which is an open source 3D engine, rendering engine, not a whole game engine, just purely the rendering stuff. There's also a physics component, but Away3D itself is purely the rendering engine. It's still the oldest, still existing open source, just 3D engine for Flash in general. And it looks like it's going to be one of the last as well, because it's Flash-based and, there's probably going to be JavaScript versions in the future as well. Just as a quick introduction about myself, how I got started. I grew up with one of these, Commodore 64, which I'm sure most people know. Mostly I played games on it, but now and then I used it to draw dinosaurs on the screen. Then, after a while, I was a really quick learner, so I came up with much more realistic dinosaurs. Paleontologists are laughing right now. They're never on conferences like this. So after a few years, I finally got my first PC when everyone moved on from their Super Nintendos. And I discovered a little program called QBasic. So I started coding just BASIC on my PC instead of the Commodore. Nothing serious, just as whatever a 12-year-old does. Draw ASCII boobs. Then I started playing video games, Doom, Quake, and basically my life was over. I got into the demo scene a bit, more as a fan, but I tried to code a bit of the same type of stuff, but nothing too successful. And then I had a bit of an identity crisis when I was 18 or something, and I decided, hey, let's fuck coding, let's start drawing shit. And that wasn't a good idea. So, but through doing this, I noticed that I actually liked working with light rather than actual drawing. That was my favorite topic. So that's how I got into contact with Flash, actually, because at first I saw it as a new way of drawing and bringing animation to a wide audience, because it was a great platform for that. It was ran on all browsers, on all platforms, so you could easily share and publish stuff. And it actually got me back into coding and brought me where I am now, doing 3D stuff. And as I said, one of my favorite topics is light, as it was with the drawing stuff. Ooh, there's water. I'm going to use that. Sorry. And that's what this talk today will be about as well. Excuse me. So basically, this talk will explain the basics of shader programming without any code. I think it's pretty useless to have a presentation just showing code, because you can learn a shader language in a day or something by just browsing the internet, and you never learn the actual concept. You just start copy-pasting. So I just want to bring you the concepts, and I think since you're mostly animation students, you already know the general idea, but know not exactly how it should translate to code, for instance. So to get started, a quick introduction of what light is. Light is basically energy, part of the electromagnetic spectrum, which means that it's basically just photons traveling through time. They're a quantum matter, quantum particles. So they exhibit both properties of particles and of waves. And every color has a different wavelength, and it's just your brains that interpret those wavelengths as colors. And images. Now, the way that light acts as quantum particles is normally you would expect if you have just like a wall with 2 openings in them and you introduce a light that the light would do this. And you would be right for most intents and purposes. But once you start reducing the scale to a microscopical level, to a quantum level, then actually the wave properties of the light become obvious. And you get these interference patterns, which are very interesting. And they're visible on surfaces such as soap bubbles, because they refract light depending on the wavelength. And then on like a highly detailed surface, like a CD, because the indentations in the surface are so small that that the wavelengths react differently on it. But that's only for like a limited kind of surface. Mostly we're going to make some simplifications because working with waves is much more complex than simply working with vectors. So instead of having a wave-particle duality going on, we just give every light photon a direction and an origin, basically a 3D vector, a position vector. And then complex wave functions that represent color, we're just going to encode that as another vector representing color, in this case just RGB. People doing linear lighting will kill me now because I'm mentioning RGB. There's better color spaces available, but let's just stick to RGB for now. And then with these simplifications, we can look at what happens when light travels through a scene. And if we're doing 3D rendering in real time, at some point we're definitely going to want to render a scene with Sir Corey Feldman sitting next to a window overlooking New York City on a rainy day, because that's what we like to do. We come from the 80s. So basically what happens is that every photon just starts out from the light and can travel like any of the spherical direction from the light. And then it can hit Corey Feldman in the face, hopefully. It can travel through the window. It can be refracted, changing direction by going through the window or the raindrops on the window. It can reflect from the window, and it can even enter Corey Feldman's face, travel around inside his skin for a bit, and then bounce out again. And the chance of that photon hitting the camera to form an image is like infinitely small, basically. So if we would render a scene this way, we would be waiting for all eternity just to render one image. And we want to get Corey Feldman on the screen as soon as possible. So we're going to take some simplifications again and take some hint from these guys. There's like 80s all over the place. And we're going to do some things backwards. That's the point of this. So basically, what we're going to do is we're just going to take our objects. They're all basically encoded as triangles. We're going to render it through the screen. And we already know the world position of that object because that's our starting point. We're going to trace back. We know the direction to the camera. And then if we have that point and the point on the screen and the directions and everything, we can start looking at the scene. Where are the lights and how are they influencing that point? And to figure out the color of that point because of the influencing light, there's a function that we use, and it's called a bidirectional reflectance bidirectional reflectance distribution function. That's it. And basically, it's bidirectional because it takes 2 directions into account, both the out vector, and that's the direction the light travels from the object to the eye, and then the in vector, which is basically just from the light to the object. And then the color, like the BRDF, the function, it depends on like surface reflectance properties, specularity properties, and all that. We'll get to that later. Just want to show this. And for a real scene, we would need to take all the incoming light directions into account, which would mean that we're encoding all the light as a function, and we need to take an integral over the whole sphere, or hemisphere at least. But for now, let's just ignore all the other directions and just define discrete lighting points into our scene. And for the lights, we're actually just using a mathematical ideal, just point lights. So the lights are actually infinitely small. So we have just a few discrete points to analyze. And then our our whole integration just boils down to a couple of sums of discrete functions. See that in action, I think. We're going to analyze the basic components of the old school direct lighting model. If you're slightly interested in the math, it's up there to the left. You can probably get more out of it if you just Google it or something. But it's there for if you're interested. Basically, this is a scene without any lights. So the BRDF is simply 0. It doesn't receive anything. There's no lights in the scene. It doesn't reflect anything. Now we're introducing like the most basic concept, which I'm sure you all know, ambient light, which is like a poor man's version of global illumination. And it's basically, because light doesn't really come from just one object, there's also like the sky, just light bouncing off of objects. And ambient light just gives like a minimum lighting value to account for that in a very, very cheap manner. And basically what happens is that light comes from all over the place. The photons just reflect into random directions, and some hit your eye, and that gives this color. Next is the diffuse component of the light. And because of the roughness of the surface, light photons won't just perfectly reflect off the surface, but just when they're, just show it. They come from the light and they just scatter in random directions, and in my demo they magically gain speed as they do so as well. That's an error. But as you see, it's just a very rough kind of reflection, and you can't really make out the lighting direction easily. And you'll notice that if I start turning the surface, I don't know if it's visible on the screen. Oh, whoops. Sorry, sound guys. Let's turn the surface, that it becomes brighter if the surface is facing the light, and darker if it faces away from the light, which is, of course, no surprise to you guys, I hope. Otherwise, I'm in the wrong room. And why that happens is something that many books that talk about shader programming just overlook. They give you, here's a diffuse function, and we're going to neglect to tell you why. And even though it's like ridiculously simple. Basically, if we look at how the light travels again, and we look at the surface direction, which is represented here by the surface normal, which is just a vector perpendicular to the surface, we can see that the actual impact area of the light becomes larger if the surface turns away. Which means that for the same amount of photons, for the same amount of energy, you start affecting a larger surface. So of course, the average energy per square meter is going to be smaller, hence making it darker. And you'll see that if the normal aligns, so the plane is facing the light, it's going to be like the brightest. And at a 90 degrees angle from there on is going to be the darkest. And basically, that's just a function of the angle of the light, which we can calculate using the dot product. Or like I have a negative dot product there because of the direction of the light in my example. And the dot product is equal to the cosine of the angle. So it goes from 0 when it's at an obtuse angle, and then 1 if it's aligned with the light. I hope that makes sense. And then we can, of course, something else I don't have to explain to you, texture mapping, which is just affects the diffuse reflections, the diffuse reflectivity color per pixel. And I think that's all I need to say about texture mapping, because you guys are doing that constantly. Specular reflections, you should be familiar with that as well. It's just the type of light that basically, wait, let me go here. It's emitted by the light, and it actually follows a clear reflection path. It's actually reflected by the surface normal, like in this direction. And the thing is, this is no physically based method. This is using Phong shading. It's not based on any real physical measurements. It's just based on the observation that the highlight is stronger in the reflectance point there if we get closer with our eye to the reflection vector. So we can really see that the reflection vector, the impact point, we can see the high bright highlight there. And of course, if we turn the surface, then the reflection vector changes and the specular reflectivity moves. It should be straightforward. Now this is again a function of an angle of two vectors, but this time it's the view vector with the reflection vector. Just like a blindfong is like a simplification, which I'm not really going to get into. It uses like some simplifications and sums of a vector, and it's not really important right now. Now, normal mapping is just another texture added into the mix to perturb the surface normal, so essentially the surface direction for every pixel, making the whole lighting calculation different per pixel, giving like the appearance of more surface detail just through using textures. We're not actually adding new vertices and etc. in there. But again, this is probably like peanuts to you guys, because you're using it as well. And then, of course, Fresnel specular reflections, which is basically a method of a physically based method of modulating the specularity, the strength of specular reflections based on the view angle with the surface. And you're going to know this. If you look down a pool of water, you're not going to see strong reflections, but once on a grazing angle, like towards the horizon, you can see everything perfectly reflected. And that's the effect of a Fresnel specular reflection. To give the example here that, wait, I lost my light. Where is it? Ah, there. So basically, at a grazing angle, you can see strong highlights there. But if you actually look down, there's hardly any. And the actual function is kind of complex. There's a relatively simple approximation called the Schlick's approximation, which is up there if you're interested. Otherwise, just remember Schlick and Google it. There's great explanations in there. Now, it's always nice to have some shadows in there because it makes things look vastly more real and gives more depth information, especially for games or anything like that. And it just looks nice most of the time. But the problem is when we're shading things, we don't have any knowledge of other objects. If we're drawing the plane and the bottom, we don't know anything about the cylinder up there. And we have, in some way, we have to introduce that knowledge, and we have to do this through textures. But let's make some observations first. If we trace a line from a point in the shadow to the light, we'll notice that it'll intersect the cylinder. And the point on the cylinder will always have a smaller distance to the light as on the plane. That's why it's in the shadow. So what we just have to do is basically render the scene into what's called a shadow map. And it's just a render of the scene from the point of view of the light, and we encode the distance to the light, the depth value of that render. And then when we're rendering this point, let's say right here, we trace the line back to the light, and we find the intersection with the shadow map. We try to find out, okay, where is this point relative to the light? And then we can read that distance, and if it's smaller, that means that there's something in the way. Otherwise, the value would be more or less equal. And if there is an object apparently closer to the light than that point, then it's in shadow, and we just don't shade it. Now, there's obviously some aliasing going on because of the limited resolution of the shadow map. There's a couple of improvements that can be done. One is called percentage closer filtering, which basically, in this case, is like a cheap version of that. It's taking 4 sample points, right, of neighboring pixels, and then it's just trying to figure out, okay, this one is in shadow, the neighbor isn't. So somewhere there must be some transition of being in shadow or not. And it's actually just the same as if you're enlarging a picture in Photoshop and use bilinear filtering, except you're doing it on comparison results rather than on pixel colors. And then you get you still have like obvious aliasing, but it's kind of smoother, it's kind of softer. And ooh, there's a bug in my shadow map. No one saw that. And then there's also a technique where we just take more samples. Just compare like in a radius and average out the value so we can get more softer shadows. And the nice thing is that we can just grow that radius. And I'm not sure if this is showing up well, but you can get soft shadows that way as well, which look much more interesting than, say, this. I think that's it for the basics. Let's see this applied in a real setting. And of course, for that, I have a dinosaur. Awesome dinosaur. So obviously, if we're not doing any shading, it's gonna look like crap. So first step, we just introduce our light. Oh no, first step, introduce textures, sorry. Still not using any lights, just using the texture color to put something on the screen. This is a texture without any baked AO or anything, just a flat diffuse. And then we introduce the light. So you already get much more lighting detail on the image, but here it's obvious that the regions in the underbelly and stuff, the dark regions are way too dark. Because as I said, there's lighting coming from all over the place, bouncing off of objects. And as I said, that's why we have ambient. And you can already see like the difference between the two is the ambient really makes it fit more in the setting, have some general average minimum light in there. Then we add the specular reflections to get the highlights. And obviously our light is somewhere there. And unless we have a plastic toy dinosaur, these are way too smooth, which is why we have the, normal map to add all this surface detail, changing the way the light reflects. And this is not changing the mesh, it's just adding in the normal map. Just another texture. We can add yet another texture to change the specular reflectivity, the strength of the highlights per pixel. So you can see the difference in, around here, them being softened a bit. Add some shadows, so if you move the light, you can see some self-shadowing as well. Really making it obvious that the dinosaur is standing on the floor and not just hovering, because this one might just be hovering a bit above the floor and you wouldn't know it. Shadows make it sure, give it more spatial information. And this is a very cheap approximation for subsurface scattering. I'll get into how that was done later on, but basically for now, just if you look at the difference, basically what's happening is that the light enters the skin of the dinosaur and just is allowed to travel underneath the skin before it exits again, brightening up some, in this case, just being used to brighten up some darker areas and having some more organic, flashy kind of shading. This in particular is a very cheap technique. I'll show you later. And then we have the specular highlights. So instead of just having strong highlights, wait, let me go to where they're strongest. We can introduce more strong highlights and grazing angles and soften them, just looking down at them, as all materials in real life do. Not sure if anyone went to the physically based rendering session this morning, but they talked about that all materials do that. So that's it for T-Rex. Moving on. Looking at reflections, we've already talked about specular reflections. And all the objects I've showed before had really soft specular reflections, just general blurry highlights. If we go to the real world, we run into constructions like this. In Chicago, I think this is. And of course, this uses the actual environment. It doesn't use idealized lights to render reflections. And this is kind of our first step into like stepping away from the only point-based lights. So what happens is, in real life, the light would travel along the reflection vector, marked R, reflects around the surface normal and travels towards the eye. Since we're doing it backwards, we're starting out with the view vector, reflecting that instead, and then trying to figure out whatever it hits and to know the reflected color. The reflection vector is calculated pretty simply down there in the corner. Again, it's also on Wikipedia and stuff like that. And to give a representation of the surroundings, because we can't just start ray tracing into a triangle scene, we're trying to do all this stuff in real time. We basically just encode the scene in a cube map. This particular example is made by Paul Debevec, like the international intergalactic captain of cube maps. And basically what it is just like 6 images, each for a side of a cube. And we throw the reflection vector, follow it until it intersects the cube, and we just sample the point, the pixel at that point. GPU hardware does all this for us. We just give it a reflection vector, a cube map, and it just returns a color, so we don't have to start looking at, okay, which side will it intersect? It automagical is what Steve Jobs would have said. And a cube map, of course, you've seen it. It looks like this, as an example. To show that in use, for me, the 90s never happened. I get stuck somewhere. So this is just a model shaded like the dinosaur before, only using direct lights. If we replace that shading model with environment maps, this is what we get. So, sure, all of you know this. You just get perfect reflections in the stuff there. My model is broken as well, actually. But, of course, unless you're the T1000 Terminator, you don't get to reflect this much. So we just take the old model, the environment mapped model, lighting model, not mesh, and combine them by just blending between them. So you get like light contributions from the discrete point lights as well as reflections, particularly obvious in here. But still, this isn't really like cutting it. It kind of looks bleh, not real at all. So we can make some observations, do some improvements by just first introducing Fresnel effects for the cube map, the environment map. So again, at the grazing angles, it will reflect more around the jaw here, and not as much when looking at it head-on, because it's kind of like a dull metal. Still, oh yeah, if you look at this, like at the eyes, there's also, because of the Fresnel effect, now a more pronounced reflection where there shouldn't be reflections because the model is self-occluding. So we just introduce another texture, which is for every pixel tells how much the reflection there should be. In this case, none at all for the eyes, or like hardly any here at the outsides, but a lot on the skull and stuff like that. And then I think there's a final thing. Using light probes, which are like convoluted processed environment maps, we can actually just throw out the whole idealized lighting stuff that was going on and use the actual environment map to provide the diffuse and specular lighting. I'll get into that later on, but for now, just you can see that the model actually like fits in much more with its actual environment, is much closer from the Terminator I remember as a kid. So that's it for Terminator. How am I doing on time? Oh, not too bad. Thing about environment maps is you can just render them at runtime as well. So if you have a scene that dynamically updates, you just update the cube map. And this is not doing that. Let me see. Come on, move R2. So you don't see any of the landscape reflecting in the droid. You don't see R2 reflecting in the droid, because we're not updating a real-time cube map. Once we start doing that, it's much more interesting, because we can actually see real-time reflections of a dynamic object. And this is done by just rendering the scene from 6 positions, just left, right, up, down, front, back, using that as a cube map, which is pretty heavy, I might add, because you're rendering the scene 6 times over. And there's, of course, some flaws with that, because you don't have any spatial information. We just project everything on 6 flat planes, and the scene isn't the cube. So if you start using it for reflections, you can see discrepancies around places like this. You can see that the reflections aren't entirely correct. But for like complex objects like this, it's usually a good solution. Now that's for cube map-based reflections. When we're working with planar surfaces, not only are the cube maps like extremely expensive because of the extra 6 renders, it just doesn't work well for mirrors, for like flat surfaces, like water surfaces, mirrors, whatever. And we can just do it in 1 render anyway. So if we make some observations again, what we see in a mirror is actually just what we would see if we were mirrored into that mirror. Whoa. Let's look at it top down, that's a bit better. But if we render the scene from the other side of the mirror, we have to make sure that we don't render anything in that red triangle, because there's nothing there. The mirror occludes that. And again, on modern GPUs, it's as simple as telling the GPU, like, here's an extra plane to clip to. Don't render that stuff behind it. In Flash, I actually had to change the projection matrix because you can't add extra planes. Was a whole lot of trickery, but it works. Wait, it was still open. So if we use a plane, let me just quickly move. We can see pixel-perfect reflections by just rendering the scene from the other side. And you can see that geometry is clipped where it intersects the mirror because of that extra clipping plane. That's it for reflections. Now, my favorite topic. Sorry, Nicola, I had to do that. If we look at these pictures, this one less obviously so, but still. What's happening is that light is actually traveling through an object, because that object isn't completely opaque, it's like translucent. And even with milk it happens, because milk lets through some light. You'll see that obviously when you put the light directly behind a glass of milk. And for instance, with skin, what happens is that light sometimes just reflects directly off the surface. Sometimes it enters the surface because of its translucency. It bounces around in there for a while before it's ejected again and travels through your eye. And in that process, it tends to discolor as well because of all the blood inside us. And I'll show some things by example rather than through stupid slides, and show some methods that can help us simulate that and show you why we could simulate that. So this is an unsubsurface scattered model, and we can immediately see that there's like a clay feeling because the shading model is very much like terracotta. And it looks stupid. Not Lee Perry Smith, whose head this is. I mean, just the shading model. And we'd like to add some subsurface scattering. Now, one of the most immediate effects of subsurface scattering is that the light exits at a different point that it entered, which means that it kind of generally blurs. It's like softened. And we can do this very cheaply by simply softening the diffuse term of the lighting model. Which, does it show up properly here? I think it does, right? Could we maybe dim the lights a bit? Is that possible? Yeah, that's good. Thanks. So, especially close up, it's like pretty obvious that it's already an improvement just by simply blurring the diffuse contribution. I was an especially cheap bastard doing this because I didn't even blur the actual lighting calculation result. I just blurred the normal map instead because it's a static model with world space normal, so I could cheat. And I used that blurred normal map in the next examples as well. Now, the second property of subsurface scattering is the discoloration when it exits the skin. And I've overdone this effect a bit, but on projector it's not too bad. So you can see like where it becomes dark, it becomes a bit red as well. And how that's done is, again, we're trying to do this real time in Flash. So we're trying to be as cheap as possible. And when we look at the Lambertian diffuse reflection that we've been using all the time, it's just a value from 0 to 1. The gradient you can see up there is just going from 0 to 1. What we can do is instead use a lookup table, just a lookup texture, custom gradient, to change the reflectivity, like the Lambert reflection color. So we can just push the dark regions away a bit, just as if the light was allowed to scatter there and brighten up the dark parts. And then we can cheaply change the color a bit of that as well, as if it's the scattered light changed color as a bit. That gradient is like oversaturated to prove a point. It's not as much in the actual render, but you get the point. And with some heavy imagination, if you look at it compared to this, you can kind of like imagine that the change is because of like scattering and whatnot. And I hope you people have imagination, so otherwise I'm screwed. Now, one of my preferred techniques to do subsurface scattering takes it a step further. And we start looking at light passing through, because let me show you this again. If you move the light behind the ears, you can't see any light moving through. In real life, light would actually travel through the ears and still be visible, even though the light is on the opposite side of the model. And this model doesn't do that. So we take a look at another observation to do cheap stuff. Basically, from the point of view of the light is more likely to travel through an object and be still visible on the other side, as long as that object is thin. This guy has an especially translucent nose, so light will travel through because that's a thin surface, but it would never travel through the entire head because there's skull, and the likeliness of it traveling through a thick object is just very small. So basically what we do is we do the same as shadow mapping. We render the distance to the light from the point of view of the light. But instead of determining whether or not something is in shadow, we also determine on how big the distance is to that point closest to the light, so we can have an estimate of the thickness of that object in that place. The red line you can see there visualizes that. And then I can show you this. Let's first move the light back. This technique just applied simply on this model. So you can already see the difference just looking at it like this. There's much more organic discoloration going on doing this. But the fun thing is that if we move the light to the back of the head, we can see like light scattering through. And also through the... Move the light through the nose. I told you this guy has a exceptionally translucent nose. But I overdid the settings, of course, just to prove a point what's happening. This technique has its artifacts. There's much more involved multipass techniques that do it much better, but just to give you an idea, many of them use similar kinds of information sets. And there's also, like, I showed you the glass of milk to show that this technique without the depth information isn't completely useless. Because if you forgive the wrong reflections down there, I used a broken version of the engine when I deployed this. So just don't look at the reflections. But if you look at this glass of milk, rotate the light. This is with subsurface scattering using that wrap method, just changing the gradient. And this is without. Okay, the colors are a bit saturated, I think. But you can see like a kind of yellowish discoloration in shadowy regions, and you can see that light is allowed to travel further through the liquid, which shows that it has some use for being such a cheap technique. It's just a simple texture fetch. Well, never say simple to a texture fetch, but okay. Now, how much time do I have? Does anyone know? Wait, okay. So I talked about this slide before, where we're taking into account all the possible directions, and this is like the hot topic in real-time rendering right now. It's trying to find good ways of getting like global lighting information, and I'm just going to show like very basic ways, very old-school ways. Like we're doing stuff like this. NVIDIA was doing this like 10 years ago. And if we would do it for real, as I said, we would have to calculate an integral over the hemisphere of all incoming lights, which is, of course, something we can't do in real time. I'm going to skip this. I'm just going to give the... Are you math geeks? Anyone? No, I'm going to do the intuition thing then. Basically, an integral just sums up all the infinitely small things that you're trying to put together, like light contributions in this case. What we do instead is limit that to a discrete set of high numbers. Imagine we're sampling this region, and we're just using one simple sample for that whole cone, sorry. And then we take that sample, we take multiple samples until we have the whole region covered with cones, and we average them out, sort of. It's not really averaging out, but it fits the intuition. And of course, the more samples we take, the closer it will be to an actual integral. And again, to know where the light comes from, we can do ray tracing, because this is a pretty expensive step. That's something you do offline anyway. You're not going to do this real time. Well, sometimes, but not. Usually you wouldn't. And so, of course, we can, again, use environment maps just for this purpose, because it's easy to show. Again, the same environment map that we can use to just take a bazillion samples. Ooh, the time lady is telling me to hurry up. So basically, let me just quickly show you this convolution going on. So just all the samples being taken. So basically, every frame, it's taking like, I think, 30 samples and averaging them out over time, because Flash has a limited instruction count, so you really have to do everything together. And then you basically, I made one for diffuse light and one for specular highlights. And that's actually the maps I used for the Terminator, the light probes. And you can do this for a couple of points in your scene and then just add them together, depending on where your model is. I'll show you this in action if it wants to run. There we go. So basically, I have 4 of those light probes in the scene for every corner of the room, and I'm like weighing them. Like their contribution is higher as the model gets closer to the corner where that light probe is. So if you look at it, it becomes more red. If it gets away, it returns to like, it uses the white overhead color. And of course, from the other side, it gets like the green from the wall. Again, this is like the runtime part, the real-time part of this is relatively like fast. It's really fast, but it's very limited. You can't use dynamic scenes, not even dynamic lights and stuff like that. And modern techniques like are investigating spherical harmonics to do that and stuff, but that's a whole session on itself. To close, do I still have time? Wait, 5 minutes? Okay. Just like I'll show an alternative rendering method. The lighting stuff is all still the same, but more and more modern engines are using deferred rendering. As I said, like in the beginning of the talk, I said we would be drawing to the screen, and then for every pixel we draw, we try to figure out where the light comes from. Deferred rendering first draws all the surface properties to various textures, and then just uses those textures to get all the lighting done on those instead of on the actual models. So basically, we can render the albedo, which is just a diffuse reflectance color. The screen space normals up right there, just to get the directions of every point. There's a depth buffer that we render just the distance to the camera from which we can figure out world positions and stuff like that for the light. And on the bottom, we have like specular, like highlight strength and glossiness. And let me quickly show a demo. Now, the stupid thing is that this is done in Flash, and modern hardware uses multiple render targets. So you can just, with one draw call, you can draw all these things to different textures. In Flash, you would actually render it like 3 times to every texture, which kind of beats the purpose of deferred rendering. But this is just for illustration purposes of what you can do with it. So this is our, like a basic, the Crytek Sponza model, which they put on their site. I broke something. Okay, so we basically render the albedo color, which is just, as I said, the diffuse reflectance for every pixel. We render the view space normals, looking around. The depth information, you get the picture specular reflectivity for every point. Like the red channel contains the specular strength, and the green channel contains the glossiness, I think, or the other way around. I forgot how I did this. It's been a while. And what we can do with this is, I shouldn't use these. Sorry, I keep switching because I'm using the wrong buttons. What we can use the depth information and the normals for is to do things like screen space ambient occlusion, which is a tricky effect to get right. In my opinion, most game developers use it all wrong, and like Crytek is actually the company who came up with this technique. They're actually using it. They're one of the few that actually use it the way it should be used, and it looks awesome. But basically, it allows for some to modulate the ambient term, just the minimum amount of light based on how much of like global light can affect any point by looking at neighboring pixels and checking their position information and inclusion information. Then you can get like interesting, like global shading effects. Sorry, this was actually the light. This is the pure ambient occlusion term. And then we can easily introduce more lights with relatively low cost because there's no overdraw for lights. We're not rendering the light for multiple objects. Okay, this is almost over. And since we have depth information and normal information and all that kind of shit, we can just use that data that we already have to do post-processing at lower cost than usual. Like, look who we have here. For instance, depth of field. Which is just if we focus on R2-D2, we can see like stuff in the distance being out of focus. Move! Where are you? There. And you can see like the foreground slowly getting out of focus. If I actually go somewhere there. Whoops. I think that's pretty obvious. And I think that's about it. So that's like a quick fly-through of basic shading techniques and such. Some are pretty old school. There's a lot of research being done like awesome research on global illumination and stuff like that. But those subjects that I tacked on at the end are really like millions of talks all by themselves. I hope it was useful. Thank you, Frank. Where are you? For having me. And that's it. Do I have time for questions, or then if anyone has questions, I'll be under this desk. How does this work? Oh, it's still on.